Gadolinium is a chemical element with symbol Gd and atomic number 64. Gadolinium is a silvery white, malleable, and ductile rare earth metal. It is found in nature only in oxidized form, and even when separated, it usually has impurities of the other rare earths. Gadolinium was discovered in 1880 by Jean-Charles de Marignac, who detected its oxide by using spectroscopy. It is named after the mineral gadolinite, one of the minerals in which gadolinium is found, itself named for the chemist Johann Gadolin. Pure gadolinium was first isolated by the chemist Paul-Émile Lecoq de Bois-Baudran around 1886. Gadolinium possesses unusual metallurgical properties, to the extent that as little as 1% of gadolinium can significantly improve the workability and resistance to oxidation at high temperatures of iron, chromium, and related metals. Gadolinium as a metal or a salt absorbs neutrons and is, therefore, used sometimes for shielding in neutron radiography and in nuclear reactors. Like most of the rare earths, gadolinium forms trivalent ions with fluorescent properties, and salts of gadolinium, 3, are used as phosphors in various applications. The kinds of gadolinium, 3, ions occurring in water-soluble salts are toxic to mammals. However, chelated gadolinium, 3, compounds are far less toxic because they carry gadolinium, 3, through the kidneys and out of the body before the free ion can be released into the tissues. Because of its paramagnetic properties, solutions of chelated organic gadolinium complexes are used as intravenously administered gadolinium-based MRI contrast agents in medical magnetic resonance imaging. Characteristics. Physical properties. Gadolinium is a silvery white malleable and ductile rare earth metal. It crystallizes in hexagonal, in the close-packed alpha form at room temperature, but, when heated to temperatures above 1235 degrees Celsius, it transforms into its beta form, which has a body-centered cubic structure. The isotope gadolinium-157 has the highest thermal neutron capture cross-section among any stable nuclide, about 259,000 barns. Only xenon-135 has a higher capture cross-section, about 2.0 million barns, but this isotope is radioactive. Gadolinium is believed to be ferromagnetic at temperatures below 20 degrees Celsius, 68 degrees Fahrenheit, and is strongly paramagnetic above this temperature. There is evidence that gadolinium is a helical antiferromagnetic, rather than a ferromagnetic, below 20 degrees Celsius, 68 degrees Fahrenheit. Gadolinium demonstrates a magnetocaloric effect whereby its temperature increases when it enters a magnetic field and decreases when it leaves the magnetic field. The temperature is lowered to 5 degrees Celsius, 41 degrees Fahrenheit, for the gadolinium alloy GD85ER15, and this effect is considerably stronger for the alloy GD5, Si2Ge2, but at a much lower temperature, 85 K, 188.2 degrees C, 306.7 degree F. A significant magnetocaloric effect is observed at higher temperatures, up to about 300 kelvins, in the compounds GD5, 6Ge1X, 4. Individual gadolinium atoms can be isolated by encapsulating them into fullerene molecules, where they can be visualized with transmission electron microscope. Individual GD atoms and small GD clusters can be incorporated into carbon nanotubes. Chemical properties. Gadolinium combines with most elements to form GD, 3, derivatives. It also combines with nitrogen, carbon, sulfur, phosphorus, boron, selenium, silicon, and arsenic at elevated temperatures, forming binary compounds. Unlike the other rare earth elements, metallic gadolinium is relatively stable in dry air. However, it tarnishes quickly in moist air, forming a loosely adhering gadolinium, 3, oxide, Gd2O3. 4Gd plus 3022 Gd2O3. Which spalls off, exposing more surface to oxidation. Gadolinium is a strong reducing agent, which reduces oxides of several metals into their elements. Gadolinium is quite electropositive and reacts slowly with cold water and quite quickly with hot water to form gadolinium hydroxide. 2Gd plus 6H2O 2Gd, O, 3 plus 3H2. Gadolinium metal is attacked readily by dilute sulfuric acid to form solutions containing the colorless Gd, 3, ions, which exist as 3 plus complexes. 2Gd plus 3H2SO4 plus 18H2O2 3 plus 3 SO2. 4 plus 3H2. Gadolinium metal reacts with the halogens, X2, at temperature about 200 degrees Celsius. 2Gd plus 3X2 2GdX3. Chemical compounds. In the great majority of its compounds, gadolinium adopts the oxidation state +3. All 4 trihalides are known. All are white, except for the iodide, which is yellow. Most commonly encountered of the halides is gadolinium, 3, chloride, GdCl3. The oxide dissolves in acids to give the salts, such as gadolinium, 3, nitrate. Gadolinium, 3, like most lanthanide ions, forms complexes with high coordination numbers. This tendency is illustrated by the use of the chelating agent DOTA, an octadentate ligand. Salts of are useful in magnetic resonance imaging. A variety of related chelate complexes have been developed, including gadodiamide. Reduced gadolinium compounds are known, especially in the solid state. Gadolinium, 2, halides are obtained by heating Gd, 3, halides in presence of metallic Gd in tantalum containers. Gadolinium also forms sesquichloride Gd2Cl3, which can be further reduced to GdCl by annealing at 800 degrees Celsius. This gadolinium, I, chloride forms platelets with layered graphite-like structure. Isotopes. Naturally occurring gadolinium is composed of 6 stable isotopes, 154Gd, 155Gd, 156Gd, 157Gd, 158Gd and 160Gd, and 1 radioisotope, 152Gd, with the isotope 158Gd being the most abundant, 24.84% natural abundance. The predicted double beta decay of 160Gd has never been observed, the only lower limit on its half-life of more than 1.3 times 1021 years has been set experimentally. 29 radioisotopes of gadolinium have been observed, with the most stable being 152Gd, naturally occurring, with a half-life of about 1.08 times 1014 years, and 150Gd, with a half-life of 1.79 times 106 years. All of the remaining radioactive isotopes have half-lives of less than 75 years. The majority of these have half-lives of less than 25 seconds. Gadolinium isotopes have 4 metastable isomers, with the most stable being 143mgd, T1/2 equals 110 seconds, 145mgd, T1/2 equals 85 seconds, and 141mgd, T1/2 equals 24.5 seconds. The isotopes with atomic masses lower than the most abundant stable isotope, 158Gd, primarily decay by electron capture to isotopes of europium. At higher atomic masses, the primary decay mode is beta decay, and the primary products are isotopes of terbium. History. Gadolinium is named from the mineral gadolinite, in turn named for Finnish chemist and geologist Johann Gadolin. In 1880, the Swiss chemist Jean-Charles Galissard de Marignac observed the spectroscopic lines from gadolinium in samples of gadolinite, which actually contains relatively little gadolinium, but enough to show a spectrum, and in the separate mineral cerite. The latter mineral proved to contain far more of the element with the new spectral line. De Marignac eventually separated a mineral oxide from cerite, which he realized was the oxide of this new element. He named the oxide gadolinia. Because he realized that gadolinia was the oxide of a new element, he is credited with discovery of gadolinium. The French chemist Paul-Émile Lecoq de Bois-Baudran carried out the separation of gadolinium metal from gadolinia in 1886. Occurrence. Gadolinium is a constituent in many minerals such as monazite and bastnasite, which are oxides. The metal is too reactive to exist naturally. Ironically, as noted above, the mineral gadolinite actually contains only traces of this element. The abundance in the Earth's crust is about 6.2 mg/kg. The main mining areas are in China, the USA, Brazil, Sri Lanka, India, and Australia, with reserves expected to exceed 1 million tons. World production of pure gadolinium is about 400 tons per year. The only known mineral with essential gadolinium, lepersonite, GD, is very rare. Production. Gadolinium is produced both from monazite and bastnasite. Crushed minerals are extracted with hydrochloric acid or sulfuric acid, which converts the insoluble oxides into soluble chlorides or sulfates. The acidic filtrates are partially neutralized with caustic soda to pH 3.4. Thorium precipitates as its hydroxide, and is then removed. The remaining solution is treated with ammonium oxalate to convert rare earths into their insoluble oxalates. The oxalates are converted to oxides by heating. The oxides are dissolved in nitric acid that excludes one of the main components, cerium, whose oxide is insoluble in HNO3. The solution is treated with magnesium nitrate to produce a crystallized mixture of double salts of gadolinium, samarium, and europium. The salts are separated by ion exchange chromatography. The rare earth ions are then selectively washed out by a suitable complexing agent. Gadolinium metal is obtained from its oxide or salts by heating it with calcium at 1450 degrees Celsius in an argon atmosphere. Sponge gadolinium can be produced by reducing molten GdCl3 with an appropriate metal at temperatures below 1312 degrees Celsius.
Please subscribe and thanks for watching.